talk is about how not to prove your election outcome. I'm Vanessa Teague. This is joint work with Thomas Haynes, Sarah Jamie Lewis, Olivier Pereira for the IEEE Security and Privacy Symposium 2020. Our story concerns the Swiss electronic internet voting system, one of the world's oldest internet voting projects, and specifically the discoveries that we made when the source code was made available, when a particular system was trying to get certification for use by 100% of voters in the cantons that decided to use it. On March 29, 2019, the Swiss Federal Chancellery and Swiss Post, which provided the system, announced that internet voting would not be available in the upcoming May elections due to errors in the verification protocol that had been discovered in the context of the open evaluation process that they'd had in place. It hasn't been available since. This is the story of why. In order to understand the story, you have to understand what they were trying to achieve. The system claimed to provide complete verifiability, and that works like this. First of all, every voter gets a code sheet with a unique code for that voter for each possible choice, for each question they're going to be asked in the election. This is mailed on a piece of paper. They vote online, sending their encrypted vote to a central server. There are 4 control components which receive votes and generate the return codes. And of course the whole idea is that the code is supposed to match the one that corresponds to the thing you chose when you voted. This voter voted no, and they're expecting to get back the code matching no that they got on their code sheet. After receiving all the votes, the control components pass the encrypted votes on to a series of mixed servers. There are really 4, but only 2 of them fitted on my slide, but you get the idea. These mixed servers shuffle the votes, and they decrypt them in part, partially decrypt them as they go. Now, it's critically important that none of these back-end components can alter, drop, or add their own votes. So the mixing servers provide proofs that they mixed and decrypted the votes honestly without changing them. And that's the subject of this talk. So the assumptions here are pretty obvious. We're assuming that the code sheets stay secret. We're assuming that the voters check their codes. We're assuming that at least one control component and at least one mixing/decryption server remains honest. And we're assuming that at least someone verifies the mixing and decryption proofs. Those were supposed to be the assumptions. And what we showed in this paper is that those assumptions were not sufficient to guarantee that the mixing servers had not altered the election outcome. We found 2 errors in the maths underlying those shuffling and decryption proofs. There were 2 different bugs. One affected the proof of shuffle and the other affected the proof of decryption. We'll talk about them one at a time. First of all, think about the shuffle proof. The MixNet used an argument of correct shuffling by Bayer and Groth, and the rough idea is it commits to a permutation matrix, proves that it really is a permutation, that is, that it doesn't add or drop or copy any of the votes, and then it proves that it has applied that permutation to the list of ciphertext that it got in order to produce the list of ciphertext that it outputs. Soundness depends on the soundness of the commitment scheme that's used to commit to the permutation matrix, which in this case depends on the discrete log assumption. Seitel and Swiss Post implemented this commitment scheme using Pedersen commitments, and these are probably already familiar to you, but we'll just review them now. You take a public key made of 2 random generators, G and H, and a commitment simply consists of generating some random value R and computing G to the power of R times H to the power of the message you want to commit to. This is perfectly hiding, and you can easily see that it's computationally binding, assuming that it's hard to compute the discrete log of H in base G. However, it's equally obvious that this is necessary, right? Because if you do know that H equals G to the X for some X, then you can easily see how to open any given commitment that you produced any other way you like. So, formally speaking, if we talk about Pedersen commitments, we would call them trapdoor commitments, because the discrete log of H base G is a trapdoor that allows you to open the commitment any way you like. So it was really important in the context of the non-interactive verification of proper mixing, that this commitment be generated in such a way that that important assumption about the discrete log being hard was met. But unfortunately, when we started looking at the documentation surrounding the system, we saw that in fact this was not the case. Here's a snippet from the documentation that came with that system. This snippet is from Seitl's specification. Instead of generating G and R in a secure way, what we see is that G and H in a secure way, what we see is that H is explicitly generated by taking a particular known value, exponentiating G to that value, and then using G and H as the parameters of the Peterson commitment. So not only does it not prove, another verifying algorithm does not check, that it's generated them in a way that it doesn't know this discrete log, it actually explicitly generates the trapdoor, and then we all have to hope that it forgets it. In fact, there are very standardised ways that this should have been done, which roughly consist of hashing G and H, and there's even a FIPS standard for how that should be done. So what are the implications of keeping, or at least not checking that it isn't kept, the discrete logarithm of H base G? Well, the short summary is, now that you can open the commitment any way you like, you can commit to that permutation matrix, prove that it's a permutation matrix, and then apply some other matrix to the encrypted ciphertexts while passing verification that everything's okay, because you can open the commitments any way you like. It took us a few hours to do the maths. It took us about 4 days to get the code compiling and running, but it's only about 20 lines of code that are modified for the simple reason that that discrete logarithm is already sitting right there in the code, and all you have to do is remember it and use it later. So in summary, this error is really a trapdoor into the shuffle proof. It completely breaks verifiability, which was a core requirement specified by the Chancellery for the level of certification that this system was trying to achieve. Exploit of the trapdoor is undetectable. In fact, the cheating proof transcripts are computationally indistinguishable from the valid proof transcripts. Now, it's probably just a dumb mistake, right? It's probably just something that somebody reading a paper that they didn't fully understand implemented in a mistaken way because they weren't 100% sure of what they were doing. On the other hand, it's exactly what a malicious attacker who really knew exactly what they were doing would do in order to be able to explain it away as a dumb mistake afterwards. But I'm betting on the dumb mistake hypothesis here. Nevertheless, it's a good thing in the Swiss case that they had some genuine, independent, reasonably open review before they used this system. So this was happening 6 months before the Swiss were intending to use that system in their later elections. Did I mention that Seitel is an international software company, however? They'd already sold the same system to New South Wales in my home country of Australia, and New South Wales was using it in their state election right at that time. We found out about these things in March of 2019. Australia was already taking votes and was intending to use it for decryption on state election day of March the 23rd. They confirmed they had the same bug, but declared that it was safe to use anyway. But wait. How did it get to this point without some kind of genuine independent review? Surely New South Wales must have some regulations like the Swiss do, mandating open public access to the source code for something as critically important as an election? No. Actually, New South Wales has a law that makes it a crime to disclose the source code to any other person except by asking the authorities first. So you can go to jail for 2 years just for telling other citizens how their electoral system works. So we're told that Seitel patched the mix server while the election server was already in the process of collecting votes. Because, of course, why wouldn't you get a firing company to patch your mixing server in a rush a week before election day? Of course, we have no way to check, but it's not the sort of thing that you'd make up. Alright, so now at least for Switzerland, we're fixing the bug, so everything's going to be perfectly secure, right? Well, hang on a minute. That mixing and decryption proof, that was a mixing and decryption proof, wasn't it? Let's have a look at the decryption part. The decryption proof uses a non-interactive zero-knowledge protocol proving equality of discrete logs. It's a very well-known technique, and they're using a heuristic called the Fiat-Shamir heuristic to make the proof non-interactive by generating their own challenge as a hash of the things they're trying to prove. So let's just review how this works. So our public info that we begin with is a generator G of the group, a public key, PK, which is G to the power of X for some secret X that the decrypting authority, the prover in this case, knows, but it's not public. And we have a ciphertext, C0, C1, and we're trying to prove that that ciphertext is a valid Algol encryption of 1. So to express that fact as a mathematical claim, we're claiming that there exists an X that we know, in fact, so that the relationship, the exponentiation relationship between the two elements of the ciphertext is the same as the exponentiation relationship between the generator and the public key. And obviously we want to do this without revealing X, because X is the decryption key for the votes. So here's how it works. We pick a random value, we generate some, effectively some commitments to some stuff, and the crucial step is step 3 in bold, where you see the prover generates their own challenge using a hash function and inputting the data from the thing that they're proving. The proof is that challenge and their answer to the challenge, and then the verification consists of checking a series of equations that map the consistency of the different things that are being claimed, and obviously checking that the challenge has been properly generated according to the hash. So this works all right if C0 and C1 are given to you, and there's a formal proof of correctness under the assumption, under the non-adaptive assumption, that the prover is given C0 and C1. However, we're not working in a non-adaptive situation here. We're working in a situation where a malicious component of the mixnet can potentially generate their own ciphertexts, and in that case, it's a serious problem that C0, the first element of the ciphertext, is not hashed. So a malicious prover can run through the whole of the proof, generate their challenge, generate Z, and then, based on the verification equations at the end, they can make up a value of C0. Oh, sorry, I should have said they can generate their challenge, then based on the verification equations they can generate Z and C0 to make the verification equations pass, even though the C0 and C1 ciphertext is not actually a valid Algol encryption of 1. So this is called the weak Fiat-Shamir heuristic, and the obvious correction is that C0 needs to be hashed instead. Now, this was easy to spot because Olivier and his colleagues had in fact already written a paper about how bad this was, because they'd made the same mistake in their Helios internet voting system and corrected it some years before. So the implication of this is a cheating mixing and decryption component, in other words just one of those boxes I showed on the first slide, can turn a valid vote into total nonsense while providing a perfectly verifying but completely false proof that it decrypted properly. In order to fit the fake proof into the mixing sequence, it needs to collude with a cheating client. It took us a few days to do the maths and a few more days to code the exploit and to check that it passed verification. Now, unlike the previous attack, this isn't completely undetectable. It does produce a rubbish ciphertext that makes it look informally as if something had gone wrong, although formally verification would pass. So, back to New South Wales again. Now it's getting closer to election day. We assumed, although remember we haven't got the source code, we assumed the same error would apply to the New South Wales system since they seem to have essentially the same system. But they put out a press release saying the Electoral Commission is confident that the new issue is not relevant to the iVote system. Of course, at the time we had no way to check. It turned out later that it was relevant, but nobody knew until months after the election when they made the code available under a reasonable NDA. There's a lot more detail in the paper, a bunch of other attacks along similar lines. Every single non-interactive zero-knowledge proof in the Swiss Post CITL code was broken by essentially the same reason. Not all of these led to exploitable attacks. One bug allowed for the client to cheat, and that was important to Switzerland because that opportunity had already been available in code that the Swiss had already used in previous elections in a precursor system. In some other cases, the zero-knowledge proofs, even if they had been patched to be sound, were not sufficient to prove the claims that were necessary to prove the accuracy of the election result. There were a bunch of other unstated assumptions, like proper generation of the parameters and other things that turned out to be important when you thought about them carefully. So as a technical story, this is really just one more example of a lesson that presumably we already know, which is that even secure protocols aren't secure if their assumptions are not met. There's nothing wrong with the Bayes-Groth mixnet, but it depends critically and entirely clearly on the hardness of computing the discrete log of those relevant parameters, and if that assumption isn't met, then it can easily be broken. In some ways, it seems to me that the political lessons are actually a lot more interesting here. Switzerland and New South Wales are stories of two countries with somewhat similar internet voting systems, indeed identical in places, and yet completely different outcomes based on the completely different quality of their regulations. Switzerland has really detailed verification requirements and strong transparency rules. And the Swiss got detailed analysis of their thing, and they're having a deep rethink as a result of what was found. Fully open public review even earlier would have spotted the bugs in the system they'd already used even earlier than they had it. New South Wales noticed there was a problem only because the Swiss transparency rules happened to have the side effect of bringing their problems to light. They ran their broken system right through a real election. They didn't tell the truth about how broken it was, probably because they didn't even understand, and they don't seem on a trajectory to improve it. New South Wales voters have to keep trusting it without any evidence that it deserves to be.